Right now, as you read this, at 1:32 p.m. on April 13th, 2026, a mountain in the North Cascades of Washington State is splitting in two. This is not the invisible, agonizingly slow erosion taught in elementary geology textbooks. This is not a process measured in 10,000 years of glacial retreat or the rhythmic freezing of centuries. This is a massive, high-altitude peak breaking apart in real time, and the only way to hear the catastrophe in progress is to press a high-sensitivity seismometer against the jagged quartz diorite and listen for the shift in resonance. In the summer of 2018, a specialized response team from the USGS Cascades Volcano Observatory and the University of Washington's Department of Earth and Space Sciences ascended a 2,592-meter spire known as Mount Sentinel, located just south of the Canadian border in the rugged Skagit County backcountry. They were not there to monitor the sleeping giants of Mount Baker or Glacier Peak. They were there because Mount Sentinel was screaming. The summit of Mount Sentinel is currently being bisected by a fracture that defies the logic of alpine stability. It is a jagged, yawning abyss, now measuring 20 feet wide, 115 feet long, and plunging over 200 feet straight down into the mountain's crystalline heart. To visualize the scale, this is a crack wider than 6 standard doors laid end to end, deeper than a 20-story skyscraper, driven like a wedge into the very foundation of the peak. Since 2014, USGS GNSS stations and laser scanning arrays have confirmed that this fracture is moving at a rate of up to 10 millimeters per month without interruption. The southern face of the summit block has already subsided by several feet. It has not slowed, it has not stabilized. The narrative often fed to the public is that mountains might fall someday. At Mount Sentinel, someday has already begun. Part of the mountain has already collapsed into the valley floor, and what remains, perched 8,500 feet above the Skagit River, is what researchers describe as a close-to-failure system. The Sentinel Ridge Trail, a popular mountaineering route ascending from the valley near Marble Mount, has been permanently closed by the National Park Service since late 2014. The risk of sudden catastrophic rockfall became impossible for the U.S. Forest Service to manage. The small community of Marble Mount sits at the base of this vertical wall, close enough that on a clear autumn day, residents can look up from their porches and see the dark, vertical line of the crack cutting through the sky. The unstable mass, held by little more than residual rock friction, is divided into at least 6 separate subunits. The largest is a single monolithic block of 148,000 cubic meters. The total volume at immediate risk is 260,000 cubic meters, enough to fill more than 100 Olympic-sized swimming pools with pulverized rock, released from an elevation of over 8,000 feet into the valley below. This is the weight of a city's skyline held in suspension by a failing internal skeleton. The clock is not just ticking, the gears are already grinding. At 7:22 a.m. on February 14, 2026, a series of broadband seismometers operated by the University of Washington's Pacific Northwest Seismic Network detected a subtle, deep-seated pulse. It wasn't a major tectonic event, just a magnitude 2.8 tremor located at a depth of 12 kilometers near the town of Concrete, Washington. In the valley, residents didn't even look up from their coffee. But at the summit of Mount Sentinel, that minor vibration arrived with a terrifying, amplified energy. To understand why, you have to look at the data generated by the USGS Sentinel Watch monitoring array. Since the installation of a 7-sensor ring around the peak's 2,592-meter summit, scientists have been tracking a phenomenon known as topographic amplification. Because of the mountain's unique tapering geometry, seismic waves from regional earthquakes don't just pass through, they are funneled and magnified. At the summit of Sentinel, peak ground velocity can be amplified by a factor of 2 to 11. A tremor that feels like a passing truck in the valley hits the fractured summit block like a localized magnitude 5.0. For a mass of rock already hanging by a thread, this is the sharpest edge of the risk. The monitoring system was designed to capture the voice of the mountain. Any solid object under extreme mechanical stress vibrates at a natural frequency, a resonant pitch determined by its mass, internal tension, and structural integrity. When Dr. Michael Dietz's team analyzed the seismic records from the initial 2018 deployment, they discovered a sawtooth pattern that has only become more pronounced as we move into 2026. Over a repeating cycle of 5 to 7 days, the resonant frequency of the summit block climbs from 26 Hz to 29 Hz. This rising phase represents the buildup of internal stress as the mountain's rock bridges, the internal crystalline connections, are strained to their limit. Then, within less than 48 hours, the frequency drops back down. Each drop represents a micro-failure, the snapping of internal supports that you can't see from the surface. But here is the data point that keeps USGS geophysicists awake. The baseline never recovers. Each cycle ends at a slightly lower structural frequency than the one before. The mountain is losing its stiffness. It is softening. It is becoming a pile of disconnected blocks held together only by friction and gravity. To see what happens when the sawtooth finally snaps, we look at the summer of 2016. On the southwestern face of Mount Sentinel, the slow millimeter creep vanished in an instant. A multi-stage cliff fall occurred, with one entire sector of the wall releasing in sequence over a single season. The aftermath, documented by aerial surveys from the Washington State Department of Natural Resources, showed a massive dust cloud choking the Sentinel Creek drainage. Between 130,000 and 150,000 cubic meters of rock, mostly fractured diorite, simply ceased to be part of the mountain. While the general public remained largely unaware, a peer-reviewed analysis published in 2024 by researchers including Jörn Lauter and Michael Krautblatter traced the downstream devastation. That minor 2016 collapse triggered more than 600 individual rockfall events, larger than a cubic meter. The Sentinel Creek, which feeds directly into the Skagit River system, was choked by sediment pulses, quantified at over 400,000 cubic meters of material. The river system is still absorbing that impact today. The relaxation time for the lower catchment is estimated at over a decade. If the primary summit block, the 260,000 cubic meter mass, fails now, it will not be falling into a clean system. It will be slamming into a valley already destabilized and saturated with debris. This creates a coupled system hazard. The downstream effects wouldn't just be a pile of rocks. They would include immediate channel destabilization, flash flooding as Sentinel Creek is dammed and then breached, and the potential destruction of critical infrastructure, including the North Cascades Highway, Route 20, and the high-voltage transmission lines that supply power from the Skagit River hydroelectric project to the city of Seattle. The USGS monitoring has identified 4 primary mechanisms driving this instability: rainfall, snowmelt, progressive internal stress fracturing, and seismic ground acceleration. Permafrost was ruled out. The summit sits just below the elevation where ice acts as a stabilizer. This means the mountain is held together by pure rock-on-rock friction. When that friction is overcome by water lubrication or a seismic jolt, the failure will not be a slow slide. It will be a transition from solid to fluid in seconds. The digital twin platform at the University of Washington now renders the summit in real-time 3D, showing every millimeter of new displacement. Every time the crack meter updates, the question remains: is this the start of the final sequence? To understand the physics of what is currently happening at the summit of Mount Sentinel, we must look back at August 17, 1959, in Madison Canyon, Montana. Near the edge of Yellowstone National Park, A magnitude 7.2 earthquake triggered the Hebgen Lake landslide. In less than 60 seconds, 80 million tons of rock, an entire mountainside, sheared off and slammed into the Madison River at 100 miles per hour. The resulting displacement wave was so powerful it surged upstream, overtopping the Hebgen Dam. 28 people were killed, and the landscape was permanently altered, creating Quake Lake. That event serves as the primary American calibration for what happens when a stable mountain mass reaches its catastrophic limit. But there is a crucial difference. The Madison Canyon slide was a surprise. Mount Sentinel is giving us every piece of data necessary to predict its demise, and that data suggests a failure mode that is far more complex than a simple collapse. The science of progressive failure is what keeps the USGS landslide hazards program focused on the North Cascades. A mountain does not usually fail all at once because of a single flaw. It fails because of the slow, methodical zipper effect of internal rock bridges. Think of these bridges as the microscopic crystalline bonds within the diorite. As the 115-foot deep crack widens, the weight of the 260,000 cubic meter block is transferred to a shrinking number of these internal supports. Every pop heard by the seismometers at the summit is the sound of one more bridge snapping. This is the concept of residual rock friction. Once the bridges are gone, the only thing holding that city block-sized mass of stone in place is the roughness of the rock surfaces grinding against each other. In 2024, specialized modeling using DCLO software, the same high-resolution simulation tool used by the USGS to model volcanic debris flows, revealed a terrifying coupled system scenario for the Skagit Valley. If the Sentinel summit block fails during a period of high saturation, such as the atmospheric river events that have become increasingly common in the Pacific Northwest, the rock mass will not simply pile up at the base of the cliff. It will enter the Yogbach equivalent drainage of Sentinel Creek and transform into a high-velocity debris flow. The Skagit River, just miles downstream, is the lifeblood of the region's power grid. Seattle City Light operates the Skagit River hydroelectric project here, a series of three massive dams, Ross, Diablo, and Gorge, that provide roughly 20% of Seattle's electricity. The historical parallel that haunts engineers is the 1958 Lituya Bay event in Alaska. While that was triggered by a massive landslide into a fjord, it demonstrated the displacement wave physics that occur when a mountain falls into a body of water. If the Sentinel collapse reaches the Skagit River during peak runoff, the resulting surge could destabilize downstream levees and threaten the structural integrity of the Gorge Dam powerhouse. We are looking at a potential cascading failure where a geological event at 8,000 feet triggers a technological and humanitarian disaster in the lowlands. USGS geologists have identified a critical cyclicity in the monitoring data. During the spring melt, the velocity of the crack expansion accelerates by 40%. The water from the melting snowpack acts as a hydraulic jack, filling the 200-foot deep fracture and exerting millions of pounds of lateral pressure. In the technical reports, this is referred to as pore water pressure-induced displacement. It is a seasonal ritual of destruction, but the 2026 data shows a new, more alarming trend. The sawtooth frequency shifts are no longer resetting during the dry summer months. The mountain is no longer recovering its tension. It is staying in a permanent state of high-frequency agitation. Furthermore, the Cascadia subduction zone adds a layer of tectonic inevitability. While the big one, the M9.0 megathrust quake, is the most famous threat, the North Cascades are riddled with smaller crustal faults, like the Boulder Creek Fault. A localized magnitude 5.5 quake on one of these secondary faults Wood, due to the topographic amplification we discussed, hit the Sentinel summit with the force of a localized M7.0. The digital twin model maintained by the University of Washington shows that the sliding plane is already at a factor of safety of roughly 1.05. In engineering terms, a factor of 1.0 is failure. We are operating on a 5% margin of error. The twists in the geological record show that Mount Sentinel has had similar fractures in the past, but they were stabilized by permafrost during the Little Ice Age. That ice is gone. The glue has melted, and we are left with a massive multi-ton puzzle that is missing its most important pieces. For Marcus Thorne, a retired logger who has lived in Marble Mount for 62 years, the mountain is no longer a backdrop. It is a predator. Every morning he sits on his porch with a pair of high-powered Swarovski binoculars, aiming them toward the jagged notch of Mount Sentinel. He doesn't look at the glaciers or the eagles. He looks at the crack. You can see the shadow it casts when the sun hits it just right in the late afternoon, Thorne says. It's a black line, straight as a spear, cutting through the summit. In 2014, when the Forest Service closed the Sentinel Ridge Trail, we thought it was a temporary precaution. Now, 12 years later, we've watched that line widen. You don't need a PhD to know that a rock doesn't heal itself. Thorne's home sits less than 3 miles from the projected debris runout zone. He is one of 350 residents living in the immediate shadow of a potential 260,000 cubic meter collapse. The human cost of this geological instability is not just measured in potential casualties, but in the slow-motion evacuation of a community's peace of mind. Doctor Sarah Vance, a senior geologist with the USGS Cascades Volcano Observatory, manages the Sentinel Watch dashboard from her office in Vancouver, Washington. My phone has 3 different priority levels for alerts coming off that peak, Vance explains. If the crack meters register more than 2 millimeters of displacement in a 6-hour window, I get a Tier 1 notification. If the seismic sawtooth fails to reset, my entire team gets a call. We are essentially presiding over a mountain's deathbed, waiting for the final breath. The logistical nightmare of a full-scale failure is staggering. According to a 2025 FEMA Region 10 risk assessment, a total summit collapse would result in immediate damages exceeding $450 million in infrastructure alone. The North Cascades Highway, State Route 20, the only major east-west artery in northern Washington, would be severed. WSDOT estimates that clearing a debris flow of this magnitude could take months, forcing a 200-mile detour for freight and tourism. But the physical rock is only the first wave. The cascading impacts involve the Skagit River hydroelectric project. If a debris flow dams Sentinel Creek and subsequently breaches, the surge of sediment-heavy water could force an emergency shutdown of the gorge powerhouse. This isn't just a local blackout. It's a destabilization of the regional grid that feeds the tech hubs of Seattle and Bellevue. Then there is the ecological trauma. The Skagit River is the only river system in the lower 48 states that supports all 5 species of native salmon. A massive sediment pulse, what researchers call a sediment slug, would suffocate spawning beds for miles downstream. The 2016 collapse was a warning shot, says Elena Rios, a biologist with the Washington Department of Fish and Wildlife. The 150,000 cubic meters of dolomite-rich debris from that event raised the riverbed elevation by nearly 2 feet in some reaches. If the summit block goes, we aren't just losing a peak, we are losing a generation of Chinook salmon. The fine silt would stay in the system for decades, scouring the life out of the gravel. The tension peaked on the night of November 12, 2025, during a record-breaking atmospheric river event. At the USGS Monitoring Center, the real-time crack meter data went red. The fracture widened by 4 millimeters in just 90 minutes. Skagit County Search and Rescue, Skagit R, was put on high alert. We had the evacuation maps laid out on the table, says Skagit R coordinator Jim Miller. We were looking at Marble Mount and Rockport, figuring out how to move the elderly and the livestock in total darkness and driving rain. You realize very quickly that against 260,000 cubic meters of falling diorite, there is no rescue. There is only getting out of the way before the clock hits zero. The mountain held that night, but the displacement did not reverse. The residual rock bridges that Dr. Vance monitors are fewer now than they were that evening. Every month since, the data shows the same relentless progression. The community exists in a state of monitored anxiety, where every low-flying jet or distant thunderclap sends a shiver through the valley. The monitoring system, while the most advanced in the United States, creates its own kind of psychological burden. The residents know exactly how close they are to the edge, but they cannot look away. The fracture remains 20 feet wide. The mass remains 2,500 meters up, and the sensors are still listening to the sawtooth grind down to its final, terminal pitch. By the winter of 2027, the USGS Sentinel Watch dashboard is projected to transition from its current state of cautionary yellow to a permanent, irreversible red. The data does not lie, and the data is no longer showing signs of stabilization. As we look into the immediate future of the North Cascades, the question is no longer whether Mount Sentinel will fail, but how much of the Skagit Valley it will take with it. The digital twin models maintained by the University of Washington's modeling teams have run over 10,000 simulations of the impending collapse. In 84% of these scenarios, the primary 260,000 cubic meter block does not fall as a single, clean event. Instead, it triggers a retrogressive failure, a geological chain reaction, where the loss of the summit block destabilizes the fractured layers beneath it, potentially doubling the total volume of debris to over 500,000 cubic meters. This is the spreading risk that researchers are now forced to confront. The vulnerability of the Pacific Northwest infrastructure is not designed for this type of acute, high-altitude mass wasting. The Skagit River Hydroelectric Project, specifically the Gotch Dam and its associated powerhouses, operates on a knife's edge. A sudden influx of 500,000 cubic meters of pulverized diorite and glacial till into the Sentinel Creek drainage would create a hyper-concentrated sediment flow. This isn't just mud, it is an abrasive slurry that acts like liquid sandpaper. If this flow reaches the hydroelectric intakes, the damage to the turbine runners would be catastrophic and instantaneous, potentially knocking a significant portion of Seattle's carbon-free power grid offline for years. Repair costs, combined with the necessity of purchasing emergency power from the mid-sea market, are estimated to exceed $1.2 billion. The corridor of State Route 20, the North Cascades Highway, is equally fragile. As the mountain continues to split, the rockfall frequency has already rendered the lower slopes a no-go zone. By 2028, experts predict that even the air above the valley may become a hazard zone during peak movement periods, as the dust from constant micro-collapses creates visibility issues and health hazards for the surrounding communities. The National Oceanic and Atmospheric Administration, NOAA, has begun coordinating with the USGS to integrate landslide-induced flash flood warnings into the regional weather radio broadcasts. They are preparing for a multi-hazard coupling, where a standard winter storm provides the final lubrication needed to trigger the collapse. The ecological endgame is perhaps the most silent yet devastating consequence. The Skagit River serves as a vital corridor for the recovery of southern resident killer whales, who depend on the Chinook salmon that spawn in these headwaters. A full summit failure would effectively pave the upper river with fine sediment, destroying the gravel beds required for spawning for a distance of up to 30 miles downstream. The Washington Department of Fish and Wildlife has described this as a generational extinction event for the local salmon runs. The recovery of the river system, according to the 2024 paper by Barboza and Krautblatter, would take decades, a timeline that the current climate trajectory does not allow. The future of Mount Sentinel is a preview of the new normal for American alpine regions. As the Cascadia subduction zone continues to build stress, and as extreme precipitation events become the baseline rather than the exception, the structural integrity of the high peaks is being compromised. This is the Alp Sense Bench lesson applied to US soil. Extraordinary monitoring produces a sharper question that no sensor can solve. We can see the millimeter of movement. We can hear the seismic scream of a rock bridge failing. We can model the debris flow in 3 dimensions with terrifying precision. But we cannot stop the gravity. The fracture is still opening. At this very second, the weight of a city block is leaning further over the abyss, held by a dwindling number of crystalline bonds. The sawtooth signal is the mountain's countdown. When the frequency trend finally turns from cyclic to terminal, when the reset no longer occurs and the internal microseismic emissions begin to cluster into a continuous roar, the interval between detection and impact will be measured in minutes, not days. The scientists will see it. The sensors will record it. But for the people in the valley below, the only warning will be the sound of the mountain finally falling silent.